Yeah, another DraftScience video presentation. Today we'll do some other dissident sort of people. Again, it's kind of a sad story, the whole dissident thing. It's kind of like the political thing. You have something obviously bad, and you have a bunch of people that can understand that it's bad, but they all propose a solution that's worse than the bad, and you're like, oh, no, don't do that. Get the right answer. And unfortunately, dissidents are even less disciplined and less restrained into some sort of rational container. And so they go off on all kinds of directions based on, oh, it looks like. So, like the double slit experiment with regular physics went all wacky because there was a bar pattern, the simplest pattern in the universe. They got totally shocked and amazed and tripped all over it and destroyed any kind of rational physics, because they had one behavior they couldn't immediately, right now, explain. Now, yes, it did, it was a couple of 100 years they sat on it, and, and they really should have been able to figure it out in all that time. But anyway, it's the way it went. That's the way the story is told, unfortunately, is they were really dumb, unfortunately. I mean, they just didn't do it right. They didn't pick up the ball that Newton handed them. Newton handed them the baton, and they just dropped it all over the place. They hit themselves in the head with it. They stuck it in their nose. I mean, they just didn't do anything rational with the baton. They stood on the shoulders of giants and were looking the wrong way. I mean, just didn't do it right. Anyway, so these people really aren't doing it right. And I don't want to be harsh or any of that kind of stuff. This guy, okay, good vibrations. He does experiments, which is great. If you have any suggested experiments he could do with his little, he's playing with 15,000 volts, something I don't really want to do. Not only because it increases your electric bill, but I tend to be a little bit sloppy. And, expedient, let's just say. I want to get there fast. And so high voltage is probably something I shouldn't play with, because even in the past, like I worked in a machine shop and played with 400, 500, 600 volt devices, and got electrocuted every day. And it's probably just not good for you. I mean, Tesla said it does something for you. It does perk you up, but it's like taking too many vitamins. Just might not be a good idea. Anyway, that's just blah 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 blah. I also have a billion things to do, and I just don't have any time to do anything. Didn't even properly dispose of this apple core. It's sitting here on the desk. That kind of thing shouldn't be happening. I should have people to take care of that. Anyway. Alright, so he starts the video with this stretching and pulling, and I don't know, whatever this crap is, which you really don't need. I mean, just get to the point already. I don't need to do this stuff for 38 seconds or whatever the hell it is. Blah, 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 blah. Yeah, thanks, but no thanks, please. And then he doesn't really get to it right away. He just talks about it, blah, blah, blah. So let's get to the part where he's actually doing it. Alright, so it's an arc, but he's put it really, really close together. Okay, so it's 15,000 volts, which means you can get a pretty good little arc, And instead, he's got the two things really close, and he sticks a piece of glass in.
I'm gonna bend it.
And it calls this bending it, but, I guess that's what you could call it.
Fry the glass.
So,
Bend it that way.
so he's fascinated by it and thinks it's interesting, and it's not uninteresting, but it's kind of a simple principle that if he put the two arcs further apart and then stuck the glass in, he's not going to bend it anywhere. Okay, so it's really just this principle that a certain amount of voltage is required to jump a certain potential. So the more voltage, the bigger the gap you can jump. So it's that simple. There's a mathematical formula for it. I don't know if it's that exact, but it just has to do with how many atoms are in the atmosphere that you can ionize. So I guess I'll just draw. So you get the idea, right? I don't have to keep playing it, right? You get the idea?
Bend it down.
So the arc is bending around the glass. but technically it's not really going any further than it would if you just put the two poles further apart. Now the interesting thing is, okay, that's a good place to stop. As you can see, it goes all the way around the glass. Does it actually go any further? Okay, then does it travel actually more distance than it would travel if he had the two poles just separated by air? And so does that add up to a longer distance? And probably it might be, and that might be worth explanation. I'm gonna do my chalk. There it is. Okay. So to the board. Just to have a conversation, just to point out what I would argue are some possible explanations for how exactly what happens with atoms and voltage, and then jumping a gap. So these are just ideas that I would say are, some are true probably, and some are probably a little less than perfect. So the first thing, we have this idea of an atom. Okay, so we know it's positive in the center, the nucleus. But this round thing is just sort of a lie, okay? Because there's nothing swirling around in there and all that kind of crap. There's electrons in positions. So you can understand that even when an atom is balanced, that has this appearance of having an equal amount of stuff and all that kind of crap, and you might just say, oh, it's a very neutral kind of atom. The fact is, from this perspective, right? If you're an eyeball looking at it this way, put an eyebrow on there, pupil. This looks very positive here, right? And then from this perspective, right where that, I can't look the wrong way, that won't work. From this perspective, it looks very negative, okay? So the negative is right here, looking right at you. So it looks negative from here, it looks positive from here. So even when an atom is neutral, it's not really neutral. It has these places where it appears to be, come towards me versus go away from me. So if an atom's traveling by, you could sort of understand another atom. So it has an electron. And, just kind of depends on what its eyeball's doing, how it's looking. Is it oriented with its little plus part, or the net minus part, or the plus part, or the minus part, or the plus part, or the minus part, right? So you could just sort of see as it comes in, the tendency is going to be for these electrons to repel, and the proton's always going to be further away. That is, the equal positive charge is always going to be further away, but it's still there, is the key fact. And from certain perspectives, certain tilts of this atom, these two positives will repel too. But the point is that there will be attraction towards these electrons. So if the electron comes in over right here, if it just happens to move into the atom at this angle, well, then it could find that to be, as long as it doesn't have too much velocity, you can understand that it could just kind of settle into this location here and just kind of stick for a while, be a very loose and weak bond. But if it comes in this way with the electron facing the electron, well, then it's likely to bounce off. And that'd be the simple argument. And obviously, with certain velocities, you could knock yourself in there, and that's that's how most chemistry works. Is you got to move atoms with heat. You got to push them into each other kind of aggressively to get them to stick to each other. Because you basically have to say, my new atom's going to hit this neutral atom. It's going to just kind of replace that electron. This electron's going to swing in, knock that electron out of here, and the atoms are going to now be connected to each other. And that would be, I think, a sensible explanation for how the process happens, blah, 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 blah. All right. So a surface is like a unique thing, right? It's a place where you have a bunch of atoms locked into each other, all right, and attached and connected with good bonds. That's why it's making a surface, is because they're pretty reliable bonds. And so we're mostly talking also about a conductive surface, a surface that can hold a charge. It could be brighter, but it'll have to do. So what's, the idea is you're going to put a charge on this that's going to make it so you can jump this gap, okay, with electricity. Okay, so one of these is going to be negative and one's going to be positive, and obviously the negative means positive, which is just so broken. Okay, so what's going to happen is, the idea is that the surface is sitting here, and so in some places on the surface, the atoms that bounce into it are going to see the positive, and some of them are going to see the negative. So you can almost understand that there's going to be, this piling up of electrons. Okay, so now we're just adding electrons. So let's just say we have a source of metal plate, and we've got some negative charge, and we're just going to put charge on the plate, and then we're going to dump the charge on the surface. So we're going to charge this up to 15,000 volts, like in the example, which means we're going to pile on a whole bunch of electrons. So the electrons can't go in, all right? So they just have to sit on the surface. Now they're attracted. They find the spots where it looks positive, okay? The little spots where the view, okay, it's in between two electrons. There's an electron, say, here, and an electron here, and it settles in here. And so what's happening is it's still attracted to the proton, and the propulsion by the electrons isn't enough, okay, isn't stronger than the attraction to the proton. So it settles. And as it's settling, though, it does push on these electrons. So it's two forces, right? There's a positive here. The electron is here. It's got a negative over here and a negative over here. And so it's pushing down this way, and then there's forces pushing this way. These two are pushing against each other. So as it moves closer to the proton, the force gets stronger. It wants to go closer. Okay, the closer it gets, the more powerful the force saying, "Come to me," is. So there's a definite pull in. Okay, but the consequence of that is that these electrons have to go somewhere. Now they can't go, they're neighbors right here, so they can't go into each other. And they also have one down here, so they can't go that way either without increasing the pressure. So it's almost like me sitting on the earth. The earth underneath me is under higher pressure. And the further down I go, the higher the pressure gets. So the idea is these electrons have to be thought of as weight. So when one shows up here on the surface, it has to be thought of as a weight pushing down on the other electrons. And what that means is the electrons back here are having, their world is changing. Their world is going from, where they're this far apart, to a world where, they're this far apart. And that means they have more stuff bouncing between them. Okay, more force. The force is compressed. Ping pong paddle. Put a ball between the paddles and you move the paddles in. The ball bounces more times, hits the surfaces more times per second, which is more pressure. So you're building up the voltage here. This is where the voltage is. The voltage is back here. These electrons are feeling the pressure. So as you pile on electrons, you're just basically saying, I'm piling on weight. The weight pushes and causes voltage to increase. That is the pressure back here between the electrons. This is the voltage between the electrons. That's the voltage. And obviously that pressure has as you build it up, it has a tendency to, create why doesn't the ground below me, since it's under higher pressure, why doesn't it shoot up? Well, it does sometimes, volcanoes and such. So it has to be in the right circumstances and it will shoot out. So now we're just saying, okay, what's the potential between these two places? So they have an opposite potential. This one can take electrons. This one has just, it's building up more and more pressure. And so now it can shoot electrons faster, right? So the more pressure, that is, the more this is compressed between two electrons, the more capacity for it to push this electron faster. So if you just understand, pressure just means velocity. So the more pressure it's under, the faster it can eject its electron. So the electrons back here want to get out of here, fast. They got a lot of pressure, they'll push through. So if I have that surface and I have a bunch of electrons piled on it, you can sort of understand that if I start to pull electrons off, that's going to create a channel where all of these electrons will move, and this high pressure will finally be realized and it can shoot electrons. But the idea is that to shoot them, it can't really shoot them very far because the electrons don't have perpetual motion and they're running into a force that's against them. So they only have a certain amount of potential to fly. But the real thing would be is the voltage is pretty much saying, if I could get, if I could get the stuff that's piled on top of the the surface, if I could get this stuff out of here, this pressure could shoot an electron and it would make it to this surface. And that's sort of dictating your voltage versus space relationship. So just understand there's this kind of a fixed relationship depending on what the atmosphere is made out of. See, in empty space, none of this will happen, so you don't have to worry about any of it. But in an atmosphere, you're basically making a conductor. So that's the next step to get to. But first, understand there's like this direct relationship between this distance, okay, charted here, and the potential, how much pressure you've built up over here. And that'll tell you, there's a certain distance that you'll go. And so that's the distance it's capable of jumping. But it can't, it's not that it can't get through the surface. So that pressure can't get out. But if I make a hole in the ground, theoretically a big enough hole, I would end up hitting the magma and it comes shooting out of the hole. I make a hole and I can have oil shoot out of the, the pressure gets out. So basically what's going to happen is that atoms in the atmosphere are just floating around, and they're all ionic in a sense, right? So basically I'm saying that atoms are always ionic in the sense from one point of view they can look different. From one point of view it can look like a negative ion, from one point of view it looks like a positive ion. But there's also the real thing of having ions, which is when you combine two atoms, you have an extra electron that pops off. And if you break two atoms, you're short of an electron is the key thing, right? I see there's so many pieces to this, and so many of them are elemental. I'm assuming you have some knowledge of this stuff, but if I theoretically had two atoms, and they're sharing an electron, right? When I break that apart, I'm short one electron. So one of them has to be an ion. One of them has to leave with short electron, or one of them takes the extra electron, you're left with an ion behind. This has 3 electrons, this one will have 4, or vice versa. So obviously, when you start breaking things off, or combining and then breaking, okay, atomic bonds, and that's happening all the time in the atmosphere. So just understand, the atmosphere is constantly exchanging electrons with the different atoms. They're constantly ionizing, blah, 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 blah. And this is sort of also goes with the fact that if I shoot ultraviolet light through here, right, through this space, this formula changes. This relationship becomes a different line. I'm more likely, I can get the spark to jump a bigger gap if I shoot a ionizing energy in here, X-rays or ultraviolet. So if I shine X-rays or ultraviolet through this space, I'll ionize more of these atoms. And that's what's really taking place. You can sort of understand that the ions, okay, the atoms now. So I have a bunch of electrons on the surface. Obviously, that's going to be sort of conducive. Lots of electrons means that a negative ion, an ion that's short of an electron, which is really a positive ion. So, the language, see, this is why they should have fixed this plus and minus. But you can't even talk about anything rationally because the signs are all screwed up. But anyway, yeah. So what's really going to happen is a bunch of atoms are going to start lining up. They're going to create little threads in different directions where the atoms are loosely bonding to each other. Okay, they're not strongly bonding, they're just loosely connecting to each other based on these extra and absent electrons. So there's a few missing electrons, and so they're creating a bunch of threads into space, almost like your hair rising. It's a bunch of threads in space. It's the same kind of idea. They're creating a bunch of threads, okay, in space, and both sides are doing it. And where the threads combine, you end up with a pathway for the electricity, and you start pulling electrons out of that area because you have a little bit of a conductor. And then once you do that, you start releasing all of this stuff behind here, and that goes right through that pathway and just disintegrates it all, blows all these atoms to bits because you're sending so many electrons through, and creates a whole bunch of light and all kinds of sound and all kinds of stuff because it's going to just blow this conductor to bits. Okay, it has a little wire, and it's going to send so much through that little wire it made that it's just going to vaporize it, right? And so that's a lightning strike, blah, 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 blah. But it's just these pathways connecting, just finding these threads and finding a way to connect them. And, some of the lightning, sometimes you'll see lightning doesn't go anywhere, it dies. One branch of the of threads will just die. It's because this evaporated. It lost the connection, and so couldn't get anywhere. And it could be that the path now is so long. If the path gets a certain length, the pressure isn't enough to make that whole distance, because it's slowing down. The electron's slowing down. As the electrons run through here, they're slowing down, and it just runs out of gas because you've made the path too long. It would have been a good path, but it's too long. Can't make it now. So you don't have enough pressure to get through to push all the way to the surface. And that's really the key to the whole thing. Is you have to have enough pressure to get to the other side, to really start pushing. Where you're actually sending electrons, exchanging them from atom to atom. You're just exchanging the electron, exchanging, exchanging. And that's the pathway. And so the exchange is happening, but only has so much energy. So, so lots of little branches of lightning will be a dead end because there's just not enough energy to keep going through the conductor. To vaporize it, to keep pushing on the atoms. All right, that's probably enough of that theory. But I'm just saying this provides an explanation for some of where does the pressure come from? The pressure comes from is that essentially when you sprinkle electrons on a surface, to them it's like mass and gravity. You're sprinkling more mass on top of them, so you're just putting like an elephant on top of them, and they're squishing. And by squishing these atoms, squishing is the same thing as making them like a spring. Now they have a real capacity to push back. Given the opportunity, they'll push back. I think that's enough of my contribution. So relevant to this spark thing, I guess I should just do that. Water. Look, my bad. All right, so musical interlude. Do 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 you do do. Okay, enough song. Now it's all wet. Good. Alright. Don't feel like pausing because it means I have to combine the videos. It's just a little more work than I'm interested in at this moment. Alright, so what's I going to talk about? Alright, so in the bending experiment, it's like I said, he's got, the electrodes can send a plasma, so it's just atoms. It's always a conductor. So just understand, this doesn't happen in space. Space, you don't get any spark. Okay, so it's key that there be atmospheric atoms that create essentially a conductor. They're just lining up like a piece of metal, and they're just providing a pathway for the electrons to hop from atom to atom. The electrons can't make the jump. They need the atoms to be there to just push. All right. So they're an essential part of the function of the pressure being released. The pressure can't be released unless you can pull the electrons off, and the only way you can pull the electrons off is to create one of these bridges that the electrons can place for the electron to go. Yeah. So this is a plasma. The spark is essentially just a plasma. It's just a bunch of gas being heated by the electricity moving back and forth, or moving in one direction, doesn't matter. So anyway, so the spark gap would be that distance, and all he's done is taken the two electrodes, right? He's put them very close together. So obviously they're jumping a potential that's really easy, really easy to jump this distance. When he shoves the glass in, he's just pushing, how far the potential can go. And so now, but he can't do that when he has it. When he starts with it further away, okay, he can't push the glass in as far. So if he has them an inch apart, you can only get maybe a little bit of a bend, and then it breaks. Because it's just about this total distance in the end. The total distance is going to tell you whether you can maintain the gap. And again, so if he's at the full maximum distance, where it's just starting to spark at this distance, this is the furthest if he moves this electrode a little bit more this way, it stops plasma. If he does that, then he can barely poke it. If he just pokes it a little tiny bit, it'll break. There'll be no more spark. So it just has to do with the fact that there's a certain length of conductor that you can make. And if you make the conductor too long, okay, there's not enough energy to get all the way across the conductor. And how much energy is just dependent on how much voltage there is. Yeah, so that's probably enough. Yeah, it's probably more details to cover, but I think that's a good enough reduction of the subject to the essential bits. So, interesting experiment. Like I said, the fact that he has this, he does lots of different things. I don't know if he's ever jumped the gap of a candle flame or something. I mean, obviously, lots of ions. You probably get some interesting effects. He's been shooting it into magnets and stuff, which, to me isn't very interesting. Because we know that these two things, although very related, you can't, the forces don't really interact. So you're still just saying, am I manipulating ions or am I manipulating electrons or protons? You really can't tell the difference. So you can't really say whether you're getting to something elemental or whether you're just, But there must be some experiments that this could reveal something, playing with high voltage. So if you have some, I'm sure Tesla already did this. All these people already zapped everything there could be to zap. So there's probably not that much room for learning something, but I'm just, I can't be sure of that. Be interesting to run an arc through a 2-slit, see what happens. Anyway, something like that. Who knows? So there really isn't anything else to this video. He doesn't draw any conclusions, and like I say, he's sort of one of these wacky, Ken Wheeler, Nuttiversey kind of people. So I can't say much about his theory. I just like the hands-on approach, which is nice. But he has all kinds of theories about swirling stuff and all of that kind of, the whole water experiment where you spin something in the water, he falls for all that kind of stuff, as if that's a reasonable explanation. When I'd argue it doesn't make any, people should be able to figure out how much energy it takes to actually swirl water. It's an insane amount of energy you have to use up to get the water swirling, right? And you get a tiny amount of repulsion or attraction out of it, like 1,000,000 times less attraction and repulsion than the amount of energy you put in. Just an insanely bad ratio. And that there's no way magnets are that inefficient. Magnets are powerfully, for their size, they're powerfully motivated. There can't be 1,000,000 times the amount of energy that the magnets are displaying, caught up in a bunch of swirly crap. Come on. Not realistic. Anyway, so so we'll move on to the next one. So this Richie guy, we've had arguments in the past, blah blah blah. He's whatever. I could put him in the category of a similar to whatever that other crank is. What's his name? I don't know. The British sound wave guy, radio guy. But anyway, so so he's making this claim that he's now invented this new propulsion system, okay, that's going to enable us to go to Mars in 3 days somehow. I don't know. And he's overcome gravity as a force, and somehow not just overcome it, but somehow figured out how to capitalize on it in some way where he can make things do these incredible quick accelerations and movements, but he doesn't say anything in this video. He doesn't give you any indication that he has any theory at all. And so he spends half the video just to get to the point where he's saying things that Newton already knew, and everybody already knows is a feature of gravity.
Kilometers an hour.
So he draws a picture basically saying, oh, it's perpendicular to the arc you're on. Yeah, of course it is. That's exactly what forces will create. But again, you see, these people all have it wrong in the sense that, all going all the way back to Faraday, who, was so good. Faraday was so good. But he made this huge mistake, in thinking, in not recognizing what, half of it's revealed later with Maxwell, where Maxwell is getting half the story really right, okay? And that is when you're analyzing charges, the idea is you recognize that this is the force, okay? So you can make this a point source. I can make this tiny. It doesn't matter how small I make it. And the idea is that it's already perpendicular to that point source, okay? And this idea, these are just straight lines. And that's the inverse square law. Just by doing this, I've already created my inverse square law. I've already explained why it exists. And so all I'm saying, all you're doing when you're analyzing a charge is you're just saying, well, how much of these? So let me draw a whole bunch of these lines. The more lines I draw, the more obvious it becomes, right? That if I have something here, all I have to do is count how many lines it broke. And it'll tell me how strong the force is, right? The closer I get, the more of those little lines I'm going to crash into. And the further away I get, you can understand, the further away I am, I might only hit one of them. And I might end up in this space for 10,000 years, and then I'll hit the line. I'll hit the little bit of force coming. And it'll be just as much force as if I was right here. It's just I'm less likely to hit it when I'm way out there. I'm less likely to hit the photon. I'm a lot more likely to hit it the closer I get, the more photons I'm going to hit, the more bits of energy. So it's all just they're all straight line forces. They all can be understood as straight line forces. And the huge, gigantic mistake is sitting here saying, well, I have these lines of equipotential, right? Equipotential. So then I can just draw circles around something and say, well, this is all minus 3 volts or something, or minus 3 whatevers. And it's the same distance. Okay, so what? That doesn't mean something's going around there. It doesn't mean something's in orbit. That's flying around in this orbit or something. None of that is necessary to understanding that this is just an arbitrary line. I can make it anywhere. I can have any distance, and I can apply and say the same rule applies. Yes, you go the same distance away, it's going to be the same amount of, at the inverse square law, this distance and this distance are equal. But that doesn't mean there's a line going through space commemorating the fact that this is an equal distance. There's no line. There's nothing traveling on the line. So field lines and lines of force, I'd say these are lines of force. These are the only lines that matter. And when you're going to figure out what's happening in gravity, all you're going to do is combine two lines. The velocity line, okay, which isn't going around in a circle, it's going in a straight line, the velocity line. And now you have the force line going this way. And you're just combining those two and saying, okay, it's going to end up there. And then the next time it's going to do the same thing. It's going this way, but you're adding a force this way, so it's going to bend it this way. And then it's going to, it's going this way, you're going to end a force this way, it's going to bend this way. The orbit's just made out of a combination of these two straight lines. And all of the electrodynamics is doing exactly the same thing. So in that sense, gravity and charge have the same fundamental elemental mechanism in that they are all radial lines, okay? And all you're really doing is combining these vectors. You're just saying, what's the vector from this object and the vector from this object? And those two vectors will tell you what the impact on a third object will be. It just, So, he's not saying anything here. He's saying, well, look, when this thing's here, the force is this way or this way. Yeah, no surprise there. We all knew that. Everybody knows that. That's not interesting at all, okay? The fact that the force is perpendicular to what would be a fake circle you could draw at this equipotential, so what? It's just basically telling you this is the real force. It's okay, it's perpendicular because the real force is coming from here. It's not this isn't a place. It really just isn't some kind of surface here. This isn't a surface. this is the cause of the effect, okay? This vector is the cause of this is the real vector. This is all just, don't even bother with these. These lines don't mean anything. This is the line that means something. And it's showing you. It doesn't need to be perpendicular to something. It's already perpendicular to this surface. All right. Do I need to say anything more on that? I don't think so. So I'm just going to play some of this because he doesn't say anything or do anything. He's just claiming he's okay. So he really doesn't. Okay, let's say I invented something. I discover something. I don't have to worry about somebody stealing it. Okay, in the sense that if I make a video, I've overtly published. Okay, and so what I've basically done is announced that I invented it or I'm the first one. And if somebody wants to patent something, they have to go through a process where they basically prove nobody's published. Nobody's made a video. Nobody's made a statement saying I invented it. So it hasn't been invented yet. So in a sense, you're securing your rights to something by overtly publishing, by basically saying this is something I found out. And if you want to have the rights to uses for that knowledge, then you just say something like, I can make radios work twice as fast, and I can make batteries out of this, and it's brilliant, and I can get to Mars in 3 days with this, it's brilliant. Well, then you've already secured your rights. See, if somebody had shown up ahead of Marconi and actually published saying, hey, I can do this radio thing, where I can broadcast a signal by doing this little twitchy crystal thing, blah, 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 then they would have had the rights. Okay, but if they left the papers somewhere else where there's no place for to prove it, it's the whole thing like, if Newton had told people, I have this mathematical, thing called calculus that works really well, for 15 years he didn't say anything about it, because he wanted to sit there and manipulate it, I guess, to see how much he could get out of it before other people got their hands on it. Or something like that. Everybody likes to, think that, okay, I'm on to something. I want to see how far I can take it before other people take it somewhere. So I could see some of that. But he wasn't doing it to preserve his patent rights or something. But you're not going to preserve your rights by hiding what you have, because then you have to prove in court when somebody else publishes that, well, you had it on your shelf. You wrote it on a matchbook cover. And now you're going to have to prove that the matchbook cover is actually 10 years old. So you're going to be the one stuck trying to prove your right to something. So it's always better to make a video, even if you don't make it public. Just make a video, okay? That's on YouTube. Put it on private on YouTube. And then you can always establish that by YouTube's going to say, yes, the video's been there for 10 years. There's different ways to establish your rights, but I'm just saying you're not really losing your rights by publishing. Publishing is a way of securing your rights. Now, if you're going to publish an idea, like I have a cure for cancer, but you're not even going to talk about how to use it, how to utilize it. So if you're not going to talk about uses, well, then somebody else can say, I thought of a use for your idea. Okay. So all you have to do is make sure you talk about the uses. So if you say you have an anti-gravity device, that makes things impervious to gravity or exploits gravity or however, he doesn't want to call it anti-gravity for whatever reason, then just talk about its uses. Just say that you could make a, kind of engine out of this and you could get to Mars, and then you've secured your rights. So anyway, just giving you a little legal advice. Publishing will seldom hurt you. You don't have to patent it. All you have to do is prove your precedent. Just prove that you got there first. If you can prove that in court, nobody can patent something that somebody else can prove they thought of it first. Okay, so if you want to throw out somebody else's patent, you just prove you thought of it first.
And then a couple of days cruising, depending on the relative position of Mars, of course.
So he's talking about getting to Mars in 2 days, and he says at G, right? So he says, 1G. 1G won't do it, okay? It won't get you anywhere close to getting there in a couple of days. So I don't even understand. 1G is 22 miles an hour, right? Yeah. I mean, 1G is 22 miles an hour. You're only adding 22 miles an hour to your speed every second. It's not that much.
And then a day deaccelerating at 1G. And it's important that we don't exceed this 1G, or otherwise people are going to suffer very adverse side effects from space travel. The physics.
Yeah. Well, if it's only going to take a day, you could do 2Gs without it killing you. You know, frankly, to get there a day earlier, I'd say go ahead, 2G me.
Side effects, and I'd like to see. I've done a lot of study in this area, and one of the smartest men around was Werner von Braun, and he had a brilliant idea of.
So that you kind of lose all credibility when you just play with Nazis. Okay, so don't make Nazis your hero. Just say something like, well, he was a crackers in a lot of ways, but something like that.
Rotating space station. It was huge. I think it was about 100 metres across or 200 metres across. It's pretty big, and he was going to create artificial gravity.
I know, but look, Newton already did this too. All right, I mean, Newton talked about hollow spheres in some respects, so this wasn't like unknown to people that you could do certain things. I mean, Newton was spinning buckets of water. I'm sure he knew perfectly well. Yeah, that's you can create artificial gravity this way. It's not a big. I'm just saying this is hardly something to give somebody a prize for, frankly.
By harnessing what you think centrifugal force is. See, here's another thing.
They're not real forces, so again, it's just your velocity in a direction again. They're just vectors, okay? There's no centrifugal force. There's your velocity in one direction, your velocity in another direction, and that's all there is. That's all there ever will be.
Look at one, and we give it a name, and that force doesn't really exist. It's centripetal or centripetal, as some people pronounce it, in your little rotating space stations. But what I've discovered is really, it's just blown me away. I've seen some pretty amazing things in my life. I've seen big giant cables as fat as your leg. I've seen them jump around due to the magnetic fields, and cables weighing tons.
Yeah. It's too bad you don't have video of any of that shit.
It's just jumping like they're nothing, just reacting to the magnetic startup current.
Yeah, frankly. Okay, so right there, you're almost saying, what are you talking about? Okay. Cables as big as my leg. You put enough electricity through a cable as big as my leg to make it magnetic. I don't think you did that, but whatever.
This machine I've built, it could be quite easily expanded. I think we're on the verge of a new frontier here. I will be building a larger model and encasing it
So let's just understand, he hasn't really said anything about what he's talking about here. He's just saying there's a magical force, and he says it's not push and it's not pull. So he's saying overtly, it's not push and it's not pull. I think you're going to be out of luck then, because those are the only two words that exist. That's the only way momentum can work, really, is there has to be a differential in pressure. That's how the universe works. I'm sorry, but yeah, that's how it works. So I don't think you have any chance of getting the right answer if you can't figure that part out.
Obviously, I've got to protect my intellectual property and not disclose the internal composition of the machine, but this is what this machine has led me to believe, that there's no such thing as a gravitational field.
So this is just so typical. I mean, there's 9,000 videos out there by all the Tesla kooks. I almost got it. Tomorrow, it's that stupid, I can't remember anybody's name anymore. Dullard, that Eric Dullard guy. Been promising the world forever, and nothing ever shows up. Ken Wheeler's even done it, right? He promised that tomorrow he's got a friend who's got this new super motor. It's going to be the most efficient motor in the history of mankind. It's going to revolutionize, blah, 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 any day now. And nothing. Zero. Nothing.
Field, a tool, we get two objects interact with each other. Mass.
So again, this whole interaction thing, it really has nothing to do with it. Gravity's just an absorption. When little tiny atoms move, they absorb energy from the universe, and anything that's around them is going to notice there's an absence of energy because they use some to move. So, and that's all there is. Everything creates its own little gravitational field in the sense that everything is cold from the universe's perspective. From the universe's perspective, I'm cold, because I'm eating energy. Okay, more energy goes into me than gets out of me because this is happening. Little bits inside of me are moving. The cells are moving for the veins and there's all kinds of stuff moving inside of me, and all that motion is real motion that used up real force for a moment of time. The force was diminished, And that's a real event, and that's what's causing the deficit in the field. That's what everybody sees. So the universe sees everything as just being material things, as just being energy sinks. They sink a little bit of the energy, and so less comes out of them. And obviously the outside world looks brighter, and we look darker. And that's just how every piece of matter works.
Mass field is that's what surrounds all objects in space, and it's only when the two objects come within.
So it's a field. So we got another person, another dissident who's saying, look, I got a much better theory, and it's another theory that doesn't have any real things in it, real forces. So he's just saying that two things are this and this, and even though we know that this and this are going to interact with each other at the speed of light, that however they're communicating, it's the speed of light is the communicator. Okay, so it takes time for however this knows what this is. It takes time, the same time it takes light. And yet they're saying, no, it's some sort of new magical force that just tells this it goes this way. It just tells it by some magical I told you to move. Right? But why would the I told you to move force, the special I told you to move force, or the special bent space force, why would it move the same speed as light? Why would it move the same speed as heat? You know, of something that we think of as being real stuff, real goo, real gunk, real something. So why do you have a force that's moving the same speed as the other gunky forces, and then you're saying, no, it's not gunk. It's some new stuff. Some new magical gunk. Come on. Two not very smart, in my opinion.
A certain distance of each other, you get tangible effects. Now, people say, oh yeah, but you can feel the gravitational field of the sun on the Earth. Of course you can. Well, what about when you go into interstellar space between our solar system and a neighbouring solar system in this?
So he said in some previous point that Newton was absolutely right, and now he's going to say something where obviously you don't think Newton was right because you think that somehow the force goes away, that it's not the inverse square law. No, that just somehow theoretically disappears.
Galaxy. Who's to say that gravitational field's going to be of any effect out there? I don't think so.
Newton. So that's one guy who would say. I would say also, yeah, that seems pretty obvious that gravity does work in the big universe. That galaxies are putting pressure on each other.
I think it's going to be negligible. It'd be like, what can I compare it to?
Yeah, that's right. You can't compare it to anything rational because we already know that what's holding galaxies together is gravity, okay? So I guess you're an electric universe nutter or something. I don't know.
It'd be like a fly buzzing at 500 metres. You're not going to hear that fly at 500 metres, but you certainly...
So, yes, you are, technically. That's the whole point. It's just that you're going to hear so little that you're not going to be able to recognize the sound, but pieces of it are going to hit you. Okay, just like pieces of starlight actually hit me. Okay, I mean starlight, 5 billion, a star, 5 billion light years away, is actually still hitting me with shit. Even though I'm 5 billion light years away, there's photons. I could just sit right here through the window and the photon will actually make it and actually hit me. Now, it might not hit my pupil, but it'll hit me. Okay, so if I was a bigger collector like a telescope, I could collect and see that a photon actually did hit me, my total surface. One of those little photons from that thing billions of light years away actually got all the way to me. To me. It's very special. But I mean, those are like, those are solid facts, buddy. You're just not going to undo those. It's a real thing that travels through real space to get here. All right? And pleasure me with its impact.
Going to hear it if it's right next to your ear. But anyway, that's my...
Right. So, but again, you're not going to hear it because you're not getting enough information. It's not that the information isn't still hitting you when the fly can be an awful long distance away, and you're just going to get your share of whatever little bits are left over. Now, obviously, sound is traveling through a medium, and it doesn't do the inverse square law. It doesn't do a lot of things, but it's still there. The fact is it's still there.
That's my hypothesis. I don't But
I mean, the breeze from the butterfly's wings, it's really there, okay? It's not much of a force. It's not blah, 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 but it does actually travel, and some of it probably travels a pretty good distance.
expect you to believe it. I don't expect you to, well,
I don't even understand what you're expecting at all. Why are you even doing this? You're just making a video saying, I have a great idea. I'm fantastically brilliant. I figured out something nobody else figured out, but I'm not going to give you a clue what the fuck I'm talking about. And I'm going to spend 21 minutes doing that. For what purpose? To build up our expectations? This is like some sort of, you're going to send me a birthday present or something, and you're just telling me, like, maybe you can do weekly installments. I'm going to send you a birthday present. I'm going to send you a birthday present. Oh, thanks. When? Yeah, oh, that's the trick. He doesn't know my birthday.
everyone's entitled to their own opinions, but these are the results of actual practical experiments. And
All right, says you. These are the results. He doesn't have any results. You didn't even draw a result. You didn't explain anything. You didn't explain how, well, my experiment demonstrates that I can turn gravity arrow this way with my special gravity reflector. You didn't even explain any of it. Nothing. You didn't even give us a hint of what the fuck you're talking about.
trust me, I repeated
No, I'm not going to trust you. No. I'm not doing that.
these experiments many, many times to get the same results. And not once.
So what? What result did you get? Again, you're saying that, okay, I basically have a device that makes something sits here, and without using a ton of voltage, I made it go like that. I made it just shoot straight up, and an insane amount of speed I got out of it. Okay, so I put in 1 volt of energy, and I get 5 million volts of anti-gravity potential. So it's like free energy all over the place. And besides that, I mean, it's really cool. Extraordinary claims. You're not even giving me an ordinary, anything even close to something like any kind of indication that you know what the fuck you're talking about at all. It's like me just saying, I walked on water. Yeah, I actually did. I walked, I put some water in a bathtub and I walked right on it. It was amazing.
Did I get any discouraging results? I've created gravitational impulses where I can make things jump, or I can make them hit the dirt with a lot more energy than they normally have by falling. I've got evidence to...
All right, so whatever, make them hit the dirt faster than they would from gravity. But did you put in less energy than gravity? Because if you didn't, you still haven't solved any of the problem.
suggest that these mass field shells exist simply by the nature of the motion of the machine I built.
Whatever. So there's no shields. There's no place where the gravity is strong and the gravity gets weak, and the gravity's strong and the gravity gets... No, there's no shields. There's no auras around the Earth or around any gravitational body. It's the inverse square law. Nobody thinks that, well, if I get in just the right position from the light bulb, it's super intense. And then if I go a little bit this way, oh, yeah, not intense. Oh, I go a little bit this way, no. Nobody thinks that.
So we're in the 21st century. We're in the...
Yeah, sadly, we're in the 21st century and people are still doing this. Still just telling their story. I saw this guy, Jesus, and he took like a fish and it was going to make a sandwich out of it, and it turned into 1 billion sandwiches. It was amazing. And then like this whale got beached, and this guy Jonah walked right out of the whale. He was like, what the fuck? You're just telling stories.
supposedly roaring 20s. I sincerely believe I've got a gravitational drive system, and I'll give it a nickname. I call it my boomerang motor.
Brilliant. It's like you've been hit by too many boomerangs, buddy. Few too many boomerang experiments that went bad. Yeah.
Or boomerang drive system. Take your pick.
I don't want to pick either one of those. I'll call it Cracker Crazy Cruck. Nutty Kooky Kook.
I'm very happy with my results, and just to give you some background, It was over
Okay, so this is it just gets funnier and funnier. I mean, it really isn't funny. Like I said, I'm not laughing. Am I? Am I laughing? No, I'm not laughing because this just ruins. It tarnishes everybody else's capacity to make any claims. All the people making noise just ruin the people who aren't.
40 years ago, I proposed growing diamonds in a magnetic field, electromagnetic field, and people said I was crazy. It took me over 10 years to prove that with X-ray diffraction results that prove unequivocally that I made diamond, and then to even go further, we made.
Well, I don't know if you did all this stuff. Why don't you just point me to those great things you did? Why don't you just show me the great thing you did? Oh no, he didn't do that.
A substance, a mineral called Lonsdaleite, which is a higher form of diamond that's 58% harder than normal diamond.
Right, so does that make any sense to anybody that there's actually this stuff out there that's 58% harder than diamond? I don't think so. I think all the synthetic diamonds are less hard.
We made that. We still got the machine. In the early 80s, I came up independently to Nikola Tesla. Without realising it, I actually built his turbine. And then somebody said, oh, no, Nikola Tesla did that. So I got right into Tesla and I read all his books and studied the man, and he was brilliant. Brilliant
I'm sorry. No sale on that one either.
engineer. He started off as an electrician also. Got a lot of time for Nikola Tesla. Some people sort of over-worship him. He did achieve a lot, just like Albert Einstein, I think.
Yeah, they're two entirely different people, right? Doing entirely different things and making entirely different claims, but go ahead, but yeah, nothing alike.
Another brilliant man. I think he did a lot of good, but...
What good? Where, you want to name that? Yeah, I don't think so.
Maybe he didn't get it all right. Maybe he made a little mistake here and there, and people are so involved in worshipping him that they're not going to want to look at the evidence. I got the evidence here.
Okay, fine. So when are we going to see the evidence? Never. It's the right answer, never.
This thing is, compared to normal human speeds, this thing is able to drive spaceships at, I'd say, easily 3 to 5 million kilometres an hour. So if you want to get to Mars quick, this is what you need. You need the drive system that...
Right, and you can get up to those speeds, just casually, no problem.
Gave me these experimental results. That's all I got to say. I will be putting up a video of the machine in action in the future. I just want to see what people think. So I expect there'll be a lot of knuckle bones trying to knock it.
Yeah, whatever. So I'm a knuckle bone. Okay. It's just whatever. You put up, like I said, a 21-minute video. You draw something so rudimentary and simplistic that, again, it's even beneath Newton physics. You could go back to Galileo and find these kind of drawings. So, you haven't said anything. You haven't demonstrated that you have any key to the function. So, what the hell? And you're expecting applause? Yeah.
Trying to bloody rubbish it or whatever. Try your hardest, because I've actually got physical...
Yeah, I can't actually rubbish it because you haven't described what it is at all. You haven't given a single indication of what the fuck you're talking about.
Proof. And you cannot beat physical proof in an experiment, especially when you repeat the experiment time and time and time again. I've been doing this experiment on and off for probably 2 years now, and it's just in the last couple of years, or last couple of months really, that I've, it was about 6 months ago, I told a mate, Peter, that, I've got a gravitational impulse, and he didn't mock me. He said, no, try it again, keep going, keep trying. So I did, and now I believe that if we can get this wobbly thing working...
All right, well, whatever this is, this wobbly thing working. So, it's already working, and you're sure it's going to work. How are you any different than any of the perpetual motion claimers throughout all of history? Any day now, I'm going to figure it out. I almost got it. It's almost working, almost.
To put out continuous gravitational energy in a vectorable configuration, this is the way to go to, not just to Mars. I don't want to go to Mars. I want to go past Mars. I want to go to that.
Laser gravity, I guess he can laze gravity, I guess. Economically, so he can create momentum out of less momentum. He doesn't have to put, he doesn't have to obey the conservation of energy rules. He can use less energy to make more energy.
Asteroid belt, that's where I want to go. That, you want to see where the riches lay, go to the asteroid belt, that's where the money is. You want to go to Mars?
Yeah, so even his dreams are kind of pathetic, right? I want to go to heaven so I can steal the rubies. Yeah, I mean, it's just kind of a putrid ambition. I want to go to the asteroid belt because it's full of gold and silver and other fun stuff. I can fill my pockets with it. Yeah, sorry. Yeah, no, that seems kind of trivial to me.
I said it's a good stopover, stop off at whatever facilities are at Mars, and then you go further to the asteroid belt, do your mining, and come back. Talk about energy efficiency.
Wow, how exciting. I just can't wait. I'll wait. Yeah, I can wait.
This thing runs on electricity, and obviously you've got to supply the electricity. It's not much. Wouldn't take much. Obviously, you do the math.
Yeah, a couple of Duracell batteries, and off you go.
A few megawatts of energy would run this thing in a scalable drive system for a large spaceship. But if you've seen that Avengers thing with the big giant...
I mean, megawatts. It's talking about a spaceship, so he's making an electric spaceship. Very impractical, really, because storage of electricity, it's, weight intensive. Rocket fuel is really efficient. Weight per energy, really good. Batteries, really bad.
Flying an aircraft carrier. Yeah, that's what I see. I see that sort of thing in the future.
So he sees the flying. I mean, a point in probably the most ludicrous moment in all the films I've ever watched. So even when, like in the 50s, they made all those B movies with these insanely silly aliens, that like have one glowing eye and they look like a big blob of pudding and they have claw arms and shit. Even more ludicrous than the silliest of the sci-fi movies, the heads with just a backbone, the brains with a backbone, and they're attacking the house. More silly, the silliest moment in all of film history. I mean, it really was the silliest moment, the flying aircraft carrier. And it was just too silly. I mean, beyond just preposterously silly, it was just ludicrously silly. It really just was the most insanely stupid plot flaw you could... I mean, didn't they know that anybody with a brain in the audience was just going to say, oh, you've just broken. I can't suspend disbelief anymore. I can't get caught up in this whole thing anymore. The whole thing is a movie now. It's the silliest of fucking goddamn stories. Why did you do that to this movie? I mean... Not that all the other stuff was all that plausible, but flying aircraft carrier, it's just too fucking silly. Yeah, very disappointing. I can't say it was very disappointing because the movies really are garbage. A little bit of chicks and tights, so that's okay. But most of it's pretty bad.
So, anyway, that's me for now. I'll keep you posted. If you're interested, give us a thumbs up. Tell your mates I'm either full-on crazy or I'm not.
Unfortunately, I mean, I don't really want to throw accusations that you're full-on crazy, but you're like 84%, 78.9% crazy. You're pretty high. You got a pretty high octane in that department, I think, to think that this is any kind of reasonable thing to do to an audience. I have the greatest thing ever, and, right over there. Yeah, it's really greatest thing ever. Boy, oh boy, is it the greatest thing ever. Yes, sir, it's the greatest thing ever. Did I tell you it's the greatest thing ever? Yep, it's great, great, great. It's so fucking great. I mean, you don't understand how if I did that for 21 minutes, people might say I'm full-on fucking crazy? Yeah, they might say that. Reasonable people could believe I'd be full-on fucking crazy to make that video.
I'd be really onto something. And I prefer it to be the latter, not the former.
Well, it's good that your hopes seem reasonable. I mean, that's a reasonable hope, so yeah. You're not full on crazy because there's at least 1% of you that can do something rational, where you realize it's good to hope for being not full on crazy. Yep, that's good. You got the story right. You know, which is the right thing to be, full on crazy or not full on crazy, and you figured that part out. But yeah, I can't get anything else right.
I really think I'm onto something. I've got several successful inventions that I've created. I've had a few stolen.
So isn't that the same cliche story? Isn't that the story of all of them? It's all been stolen. It's all the government took it. I can't talk about it because the government might kill me. I mean, these are just such fucking silly stories. I mean, damn, see? So that's the full-on crazy part, that you think that's a credible thing to say on planet Earth. You know, I have a real Sasquatch suit. Yeah, that didn't have a zipper in it.
Had my kudos stolen. Worse than getting your IP stolen is when people steal your kudos and they say, oh, look what I did. And you know damn well
They stole his kudos, whatever that is. So he had a kudos and somebody stole it. I don't know if that's like a bird or something.
they come to your house, they're looking over your right shoulder, exactly what you did, and the next thing they're on TV. And you know who I'm talking about. You came to my house, you stole my idea, you went on television, you told people how bloody good you were, and have you done anything since then? Nothing.
Well, who did that? Elon Musk? I mean, who are you making the accusation against? I mean, if it's true, you know, why don't you just make a video calling the guy out publicly? You know, because if it's true, they can't sue you, they can't hurt you. You know.
Because you bloody stole me kudos, mate. That's the worst thing ever. Steal somebody's credibility and just crap on them. Anyway, that's my little whinge for now. That's my updated theory of mass fields causing gravitational effects.
Wow. Mass causes gravity. Yep. Mass moving, though, would be all you have to do is add a little extra word. Mass moving causes gravity because movement absorbs energy.
No such thing as getting pulled together or pushed together from behind. There's your...
See? So what is the other choice? Okay, if I'm not pulled and I'm not pushed, what's the third option? Magical fairies. Oh, no, magical fairies would still be pushing or pulling, so that won't work. What do I have? Push, pull, push, pull, push, pull, push. What goes in between push something and then pull? What would that third thing be? Magic?
90-degree line right there, like an induction, it is like an electric current and a voltage. That's all it is. But it's not
they're just point sources. So Earth is a point source, the sun's a point source, charges are point sources. Everything has a center of gravity, so to speak, a center of their effect on the universe, blah, 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 blah.
Electromagnetic. It is mass. It's a mass field, and the product of the two mass fields, or it might even be four mass fields.
All right, so now he's really going, this is where you're getting all wacky again, you know. You're doing the full-on nuttier thing here, you know. It might be 6. Well, it could be 48 different fields, actually.
Well, I've still got to determine.
Yeah.
There could be 2 fields per object in space. This could have 2 fields, and this could have 2 fields. And the colours are...
Well, frankly, that's getting a little closer to it, but the 2 fields, actually, one of them is inert to the other one, so they balance out. You know, there's only one field, you know, there's a negative field and a positive field. You could say a proton field and an electron field.
Subscribe to these green and orange. Magnetic's already got red and blue. Sometimes voltage has got red and black. This is green and orange.
So the Earth is orange and the sun is green, so that won't work at all, frankly. That's just absolute nonsense. The gravity the sun's making is exactly the same color, exactly the same stuff that the gravity the Earth's making is. It's all the same. So that's just nonsense. You're not going to get anywhere with that notion.
Leave that with you, and have you think about it. And when it clicks, you could give us a call, see what we can do. Anyway, that's it for now.
I don't even know what that means. When it clicks. This video is based on research carried out between 1983 and 2021. I don't think so. If you would like to contribute to my research, you can do so by sending me some Bitcoin. So he goes for all the the silly shit. So that's sort of like asteroid mining. I mean, Bitcoin is clearly just a pyramid scheme for idiots. Okay, I'm going to steal somebody else's money. That's the only way it can ever work. Okay, it's a pyramid scheme. Some people will get rich and some people will get poor, and that's all you're ensuring. There'll be as many people losing money as there are people making money. Wow, brilliant. Great strategy. That's not the definition of productive.
Hope this year turns out better for everyone. This year almost broke me, I tell you. So this coming year, the one we're in now, I hope it's all good for everyone. All right, cheers. Talk to you later.
Not likely. Oh, he put his copyright on it anyway. So anyway. Yeah, it's just, frankly, like I said, dissidents are just so bad for business. I mean, the business of being somebody telling the truth, there's just so many people not doing that. The business of let's do the fact-checking thing, there's so many people who aren't checking any facts. They're just making up crap. All the conspiracy kookers and all the rest of it, this is a terrible, awful world to attempt reasoning in, because there's so many unreasonable people. So anyway, this is depressing. So, that's all. Just depressing. So, just press the button and get the hell out of here. So anyway, I do have a video, what is gravity? The sensible answer, something like that, in the subject videos. And, gravity is it's so simple. It's just so simple. But you're not going to undo it. You're not going to... There's the force, energy is a real thing. And if something's imbalancing happening, you have to create another imbalance to combat it. And the imbalance has to be made out of real energy. It can't be made out of fake energy. So unless something is, unless there's a dinosaur walking in the direction of the house you want to tear down, you have to exploit something that's already doing something if you want it free. If you want it free, you have to exploit energy that already exists. And you're just not going to find the anti-gravity force, because there isn't one. Just a fact. Alright. Till the next time, this has been a DraftScience video presentation.